forms intermediate and then attacked by another x minus. Okay, it forms intermediate attack behind. That's why it's a trans. If it's already the same direction, we call it syn direction, SYN. If it's opposite direction, we call it anti-direction, anti-direction. Syn, anti. 빨리 와. Same direction, double bond, same direction, syn addition. If it's from the behind, it's anti-addition. So this is typical anti-addition. That's why it's a trans. Okay, polymonium OH attack, it forms one bromo, two hydroxy product. It's anti-addition. Okay, first of all, Cl2 still activate double bond, hydroxyl attack here, then 1Cl, 2 hydroxyl, that's what I call halohydrate. Here, 1 halo, 1 OH means of the same position. It's not, right? It's a 1-2 position. Halohydrate is specifically, that means 1 halo, 2 hydroxy. That's a halohydrate. Okay. Okay, that's a reduction and hydrogenation that makes alkane. Oops. 클릭을 잘못했나 보지. That's a syn addition. 왜요? 이거는 클릭이 맞고 이건 틀리고. 그리고 하나만 몰라? 하나만. 문제가 있는 것 같은데. It's a metal surface. Hydrogens activated together. Double bond approaches is the same addition, same side addition, right? That's a syn addition. H. 하나만 몰라? That's also syn addition. BH2H go together and attach to the same position. And BH2 is removed later. So this reaction is the first step of hydroboration. Hydrogen borane heading together from the same side. It's not entire. Oxymercuration. mercury act as an acid instead of H plus, that coordinate, and then hydroxyl attack behind. So the whole reaction is the hydration. Water is already introduced. Now we need to remove mercury without any trace. That's a reduction condition. And that reduction condition example is this. This is the oxidation condition. Okay? So just to remove metal reductively. That's oxymercuration. Because hydroxyl already first step is added. Mercury intermediate, hydroxyl attacked. Already hydroxyl is there. You don't want to have another hydroxyl. Okay? That's why you need to cleave this reductively. Okay, hydroboration, HBH2 is added first. And for this BH2, you need to replace this with OH. To do that, you need to give oxidative condition. Okay, OH introduction point is different. These two reactions, one is Markovnikov, the other is anti-Markovnikov. Hydroboration is anti-Markovnikov, right? And the introduction point of OH is different. That is determined by this hydroboration case. Oxymercuration, water was, from the beginning, it was there. And this condition is to remove mercury. Okay. Okay, the question is whether this is a Markovnikov or anti-Markovnikov. Okay. Most of those common conditions are Markovnikov. This one basically the same. Right? And oxymercuration, here, mercury acts as H plus. That's why this is the same condition. And this reductively remove this H2 plus. This is hydroboration. This is the opposite side. Less hinder the side, BH2 is added. And later, this BH2 is replaced by OH, oxidative grade. Okay? So again, metal, if it's metal itself, what is the character of that reagent? Reductant, okay? Giving electron. If it's metal ion, that's acid. It's stabilized already. Just electron form. Okay? Any metal, in general, 99%, you can say same way. Metal powder, reductant. Oxygen, oxidant. Hydrogen peroxide, stronger oxidant. Okay, that's a planar. Which is a linear? In organic molecules, which is a linear? 2 point we don't call linear because any 2 point is anyway line, right? At least a 3 point linear. What is a linear compound? Okay. Which one is a linear compound on 3 point? SP. In compound name wise? Alkyne. Okay. Alkyne case, how many atoms are on the same line? It's a 4. Okay. So 4 atoms are on the same line as SP, and alkyne case is a linear. Okay. Okay. So based on this, let's move on to the next reactions. Now we move into oxidation. As you see here, if you don't review, it's getting more and more difficult. If you have a reasonable amount of review, then you can catch, you can fill out the missing point. It can be interesting. Okay? To enjoy this class, it's up to you. Okay? 미리미리 조금씩이라도 벌써 해. 그래서 수업에 70~80%라도 맞추면 따라오기가 쉽고, 절반 이하만 맞추면 그러면 이제 머리 아프고 괴로운 시간 많으니까 미리미리 복습해. 지금부터 계속 새로운 것들이 나올 테니까 keep up. Okay, oxidation. Oxidation, there are several different ways. These reasons we are going to learn today. Okay, at least 5 different cases giving you a different product. Okay, peroxide H2O2 is hydrogen peroxide, OO reagent. Ozone O3. Oxygen molecule is O2, is O3. And osmium tetroxide, permanganate, periodate. They have many oxygen there. Seems like they are oxidant. But depending on the structure, they behave differently. So let's go with the peroxide first. Peroxide. So basically, ROOH is similar to hydrogen peroxide. If you give that, then double bond, pi electron, donate those electrons, 2 electrons was donated, and you capture 1 oxygen atom. It forms this kind of product. Anybody knows name of this structure? This is alkene. This is called as epoxide. Okay. So this kind of you can purify it, it's kind of a product, but it's also quite a reactive species that usually is used as an intermediate for the next step reaction. So structure-wise, this is similar to bromonium. Bromonium is a positive charge, it's more unstable, it's difficult to isolate. This is you can isolate, but it's also reactive. Okay, this is epoxide. Mechanism is something like this. So now this is peroxide reagent. Looks like a little bit, but basically if you all of this motif, if you call R, okay, basically that is form of this. Okay. H2O2 is hydrophilic, very well soluble in water, but in organic solvent it's difficult to dissolve. That's why I just add this kind of a big motif, big alkyl group, to make it hydrophobic. Okay. Basically this one, M-chlorophenoxy MCPBA is called, but basically this is the ROOH. And by trying different the alkyl group, when this group was introduced, you can crystallize it. So it's easy to prepare. That's why this is popularly being used. Basically, MCPBA is ROOH, peroxide reagent. And double bond peroxide, and this oxygen was added from the same direction. It may be difficult to make it anti-direction, right? Double bond here, oxygen 1 molecule come in. If it's anti-direction, then 1 should be distorted. So it may be natural to go from the same side. Mechanism. Alkene is a nucleophile, is electron donated. This pi electron is donated to one of the oxygen, and then this push out. Forget about this part for now. This electron was donated to this, and then this is pushed out. And then it forms OH is attached here. And then this OH, H can be removed as a proton, that's a O minus. O minus, this position, this is attached here. OH is attached here. This is positive charge, top cation. And then O can match. O minus can close the ring and to make this product. We said that this is oxidation. Which part is which step is oxidation reaction? Oxygen, O2. What is the oxidation number? O2. 0. O2 is 0. It's the same atom connected together. Product here, this oxygen or any oxygen here, usually they are -2, right? They are stable forms. How about the H2O2? That oxygen, what is the oxidation number? That's -1. That's in between oxygen molecule and stable O2. Okay? Then which step is oxidation reduction happens? It was -1 here. Now by taking this electron, one electron is donated here, this electron was given to this. So originally they had only -1. Through these two electrons, one given here, one given here, permanently, make those oxygens -2. This is oxidation reduction technique here. This one donate, that's why this is reductant. And this oxygen is -1, it becomes -2, that is reduced. Okay. So through these reactions, hydrogen peroxide, it forms epoxide. That's one reaction. Any kind of hydrogen peroxide with alkene, it forms epoxide. Now, to make epoxide, another method is also possible. So this reaction we have run. X2, it activate this, and then add water together. Then water is added here, anti-addition, because chlorocation here forms triangular structure. OH attacked from behind. Okay. So in this case, this was formed on the bottom, and the OH attacked from top. OH up, Cl is down. Halo hydrate. Okay. One halo, two hydroxyl compound. So that reaction we have learned. In this case, if you give strong acid base, then this deprotonate this proton, and then this becomes O-. Then it can attack from behind and then push this out. Then product is this reaction is smoothly happens because chloride and OH group is anti. It's easy to attack. If it's just on the same side, it's difficult to attack. Even though it attacks, it cannot push this out. So that's why it's anti, it's easier. Attack from behind, this chloride is removed. Okay. So this is another way to form epoxide. So we learned two things. Now once we have epoxide, two ways we learned. Peroxide, we add 4, starting from the halohydrin, and by treating with a base, let them attack, and forms epoxide. Now here if we add the water, either acid catalyzed or the base catalyzed. Now water can attack this. If water attacks, what product do you expect? When it was a bromonium intermediate, water attack, one hydroxyl, one bromo. Right? Now oxygen is here. If water attack, water comes from behind here attack, and then ring open, and it forms dihydroxyl compound. 1,2-dihydroxyl compound. Makes sense, right? Addition forms from here, what do you think? Is it syn addition or anti-addition? Syn addition? I said OH attack here, ring open, from behind the attack, this opens top. That's anti, right? Anti-addition. So the stereochemistry is similar. This is anti-productive forms. It's very similar to bromonium case. Bromonium case, it forms this kind of a cyclic intermediate, and then OH minus attack from behind, either OH or another the halide. If there is no water, then dibromo. If there is water, then water attacks. Product, anti-product. Okay. Anti or trans product. Similar mechanisms. So organic chemistry is interesting and in a sense easy to follow because it has its own logic. If you think about how it can happen, then forming cyclic intermediate, and then attacker, nucleophile, coming from behind, then attached here, it's open here, then this is anti-additions. Okay. So So bromonium and epoxide behave similar. Okay, so we are done with the peroxide. Now moving on to many oxygen species. OSO4, osmium tetraoxide, very expensive. And osmium tetraoxide, if you add, it has OS and 4 oxygens. Okay, I have 2 oxygen behind and 2 oxygen here. Double bond there. I can attach like this. Syn addition. If you attach, it forms this kind of intermediate. Attach the first, and then reductively cleave over here by adding reductant. So there are different kinds of reductant. You don't need to memorize all of them, but you need to know this is reductant. Okay? So by adding this reductant by sulfide, then cleave over here by reducing this OS. Then it leaves 2 hydroxyl groups. Now if you compare epoxide ring opening, what is the product? Was the anti or syn? It was anti. Epoxide ring addition, ring attack from behind, it was anti. In this case, 2 oxygen was added from the same side. Product is the same product from the same direction. Okay. So that's OSO4. Double bond, and 4 out of the 4 electricity, 4 oxygen, so 2 oxygen was added. And I said OSO4 is very expensive. And it's very toxic too. Our eyes has a lot of double bond conjugated system. OSO4 especially can react with the eye, our pigments in our eyes. It can be dangerous reagent. It can attack our eyes. So OSO4 expensive and toxic. That's why if you do these reactions, OSO4 if you add, then benzene is too stable, it doesn't touch. This double bond is attacked, the product is this syn hydroxyl, 2 hydroxyl group. This is product. During this reaction, if we add another oxidant, so-called NMO, then this oxidant itself is only 1 oxygen. That's why it cannot react with this to provide this. OSO4 has 4 oxygen together, that's why it can react. But this one is a stronger oxidant than OSO4, that's why it can regenerate this product to this. So it's regenerating this reagent. Through these reactions, this becomes OSO2, reduced form. And NMO can reoxidize it to make more OSO4, and then it can go to this reaction. So this is kind of recycling of expensive reagent using cheaper reagent. Okay. Then you can use catalytic amount of OSO4, very small amount, and cheaper reagent you can add more, and you can recycle of the reagent. So why this reagent cannot do this reaction directly? It has only 1 oxygen. This reaction requires 2 oxygens. Okay? So that's why OSO4 can do these reactions. OSO4 reaction. Now, ozone. O3, if it means, it forms this kind of intermediate, and then somehow it is rearranged to form this. But it's not important, and you may form many different intermediate entities. So O3 is a reactive oxygen species. O2 does not react directly with the double bond. If O2 reacts directly, then in our air, 20% of the reagents are molecules are oxygen. None of those alkene may survive. So that reaction is very slow, but O3 is very reactive. It forms this kind of intermediate and rearranges somehow. And this condition is a reductive condition or oxidative condition. Metal powder is a reductive condition or oxidative condition. reductive라고 처음 시작할 때 무슨 학교 시작했잖아. 안 그랬어? Is that reductive condition or oxidative condition? 저기는 배터리가 또 다르고 배터리 금방까지. Okay, this is the reductive condition. So by adding ozone reagent and then reductively finish, then somehow they break in the middle. And then the product is reduced, is reductively created here, then these oxygens are attached to one here and one here. Then ketone or aldehyde is formed. Now, difference from OSO4 was OSO4 did not break the bond, right? OSO4 is just provided two oxygen each. They formed hydroxyl, one to hydroxyl. Ozonolysis means by adding ozone, lysis means breaking. By adding ozone, you break it, that's ozonolysis. Hydrolysis, by adding water and you break it, that's a hydrolysis. Okay? One side OH, one side H, and you break the bond, that's a hydrolysis. This is ozonolysis reaction. Two ways you can do, oxidatively or reductively. If you finish that reductively, they generate ketone is the same in both cases. But if it's H, then it finishes with the aldehyde. If you cleave that oxidatively, it generates further oxidized product. What is the oxidized product from aldehyde? You drink ethanol, it forms acetaldehyde. The next step, carboxyl acid, acetic acid is formed, right? Oxidatively cleaved, then it goes to the acid state. Reductively cleaved, it stops in the middle, in aldehyde. Okay? By adding ozone, it forms this kind of intermediate, and you have two ways of the finish. Reductively, oxidatively. Reduction reaction, today we have learned one metal, the other borohydride, BH4, those are the reductive conditions. Oxidative, hydrogen peroxide is oxidative. Okay, so double bond. You added ozone, and reductively you finished. And it breaks up in the middle, and oxygen is added on one side and the other side. There is no aldehyde, so this is oxidative, reductive, it doesn't matter. The product will be given on both sides. Okay. Now if you look at here, it does not attack this kind of CO double bond. Last time we have seen hydrogenation that prefers H2 addition is only to the CC double bond, not CO double bond, right? Ozonolysis is similar. Ozonolysis, it attacks only carbon-carbon double bond. Break in the middle, and then provide oxygen here. In both cases, this is aldehyde, H there. That is product ended as aldehyde because the condition was a reductive workup. If that was oxidative workup, like a hydrogen peroxide or permanganate, oxidative workup, then product is acid. Okay? So that's ozonolysis. Ozonolysis, if you capture that word in mind, by adding ozone, break it up. Lysis means breaking, okay? And oxygen giving to each side. Okay, next reagent. Even stronger oxidative reagent, permanganate. Permanganate is a common reagent when you do the oxygen generation experiment when you are middle school student or primary student. It has a lot of oxygen. This is a very strong oxygen. Maybe most stable, one of the most stable, strongest the oxidant, permanganate. If you have permanganate, you break it up and both sides fully oxidized. Break it up here and it could form aldehyde, but this is the oxidative condition, is acid. The other side, only single carbon, it could be forming acid. If the forming acid further oxidized, it forms CO2. If you cleave that ozonolysis and cleave and reductively work out, then you may form formaldehyde on right side. But if this is oxidatively free, then you may form formic acid. Further oxidative conditions, this is also aldehyde form. So this is decomposed CO2 and H2O. Okay, so formic acid, further break it up, then it forms. So this one, in a sense, you can write H2 CO3 탄산, carbonic acid. Okay, the strongest oxidant for manganate, and for iodate, slightly different. IO4 minus. That make this kind of a cyclic intermediate. And then, in contrast to OSO4 provided a 2OH, and that reacted with the double bond. For iodate, reacted with the 1,2 dihydroxyl compound. And then they make this kind of a similar cyclic intermediate. And then it is a breaking in the middle. And then providing that oxygen, one double bond here and one double bond here. It finishes those reactions with aldehyde or ketone. A little complicated, but this is most likely this is the last one. So let us summarize. We have learned hydrogen peroxide forming epoxide. Ozonolysis, break in the middle, and then depending on the conditions of workup, reductively they generate aldehyde, oxidatively acid. Okay. OSO4, providing 2-hydroxyl from the same side, syn addition. Okay. Permanganate, MnO4, very strong one, break up any double bond and oxidize the product, all acid. IO4, for iodate, that does not react with a double bond, that react with the alcohol, dialcohol. And then end result is a breaking up in the middle, and then generating aldehyde. So this reaction seems like it's a two-step reaction. One step reaction is starting from double bond, OSO4 reaction, and then generate diol, and then break this to make this aldehyde form. So this is two-step reactions. If you replace this reaction with the other condition, what condition can you use among what we have learned so far? Starting from the double bond, product is aldehyde. What condition could you use? 이렇게 배우지도 않았잖아. 다섯 개 배웠어. Among 5. Which reaction is equivalent to these two-step reactions? From double bond, OSO4 reaction, osmium tetroxide to introduce diol, and then for iodate reaction to make this product. Okay, break in the middle and then generate the 2 carbonyl compound, CO double bond, and reductively finished, making aldehyde. Which reaction is equivalent to these two-step reactions? BH3 and the BH3 added, and then H2O2, you can add OH to the BH position. That's a hydration reaction. Giving only one OH group, that's a hydration reaction. 현서야?
네.
넌 모른다고 그러지? 왜 모른다고 그러지? it's equivalent to ozonolysis. With a double bond breaking up and reductively with the recover, then product can be aldehyde. Okay. So this reaction can be two-step reactions. Maybe from double bond to form this, you use OSO4. And then to break this bond in the middle by adding iodate and finish up here, and the result is aldehyde. That means it's a reductively finished. Okay, now this. If this two product was formed by ozonolysis, by adding ozone and then reductive workup, then what could be the original compound? What is the starting material for ozonolysis? Class-wise? Okay, not that specific names. Compound with a double bond, alkane, right? So for double bond, it can be broken by ozone. So this product is broken in the middle somewhere. That means you can reconnect these two, and then this may be starting material. Ozonolysis is break up this double bond, and then add one oxygen here and one oxygen here. Okay. And here, this is the aldehyde. That means this reaction can be done go this way by giving ozone and reductive workup. Then you can finish up with this aldehyde. Okay, oxidation, we learned the 5 reactions. A little many, but you can manage it. Those 5 reactions have different product and different properties. Okay. Now move to next one. Carbene. Carbene is a little funny reagent. It looks like this. We have seen so far. Alkyl group. Alkyl group, it can be alkyl radical or alkyl anion or alkyl cation. Carboanion, carbocation, and radical. But carbon has only, all of these guys has 3 branches, but carbene has only 2 branches. And it has 2 electrons on the surface. That kind of reagent we call carbene. This can be formed in a funny way, starting from the chlorochrome. Chloride is electronegative, so they are attracting the electrons. If you treat this with strong base, first of all, OH minus attack this proton, remove the proton, and it forms this kind of an anion. And then this anion, this electron can be given to the chloride, and it can form CCl2 and neutral species like this. So this kind of reagent is called carbene. Chloroform, usually we can use it as a solvent too, but under very strong base conditions, it can form this kind of reactive species, so-called carbene. If carbene is formed, so carbene structure is very similar to carbocation. Carbocation, 3 branch, and then it's empty, and this is sp2 structure we have learned. And very similar to this, no branch, but lone electron is on this plane. This is the planar structure, and then empty pi electron there. This is the carbene structure. Now if carbene meets with double bond alkene is the electron donating nucleophile. 2 electron is available. Carbene has also 2 electrons. It comes in and then attach like this. 2 electron donate and 2 electron coming out. They meet together to make this bond. This bond. Cyclopropane structure. This is similar to epoxide. Right? Epoxide, 1 oxygen was added here. That's epoxide. This is the cyclic alkane. Cyclic propane forms these triangular structures. with the 2-chloro because the starting material was a chloro. So this is very unique reaction to form cyclic propane. Still remember ring. Still remember ring usually it has very high energy because of a ring strain. It's difficult to form. This is quite unique reaction to form this. So if you see chloroform with a strong base, now you should think, and HCl is removed, they can form CCl2 carbene, and they can be attached here to form this. So this is a unique reaction, that's good, but the problem is, sometimes if we want to have cyclic structure but without any chloro, just only carbon, that's also sometimes we need to get. Chloro is easy in this case because of this chloro, carbene was easily formed by this condition, but sometimes we don't want it. So some modified reaction is this. Starting from CH2I2. And then here, add metal. Is this reductant or oxidant? Or acid or base? Don't know. Okay, we promised to call this reductant. Okay, metal powder. This is reduction condition. By reducing this reagent, and it forms CH2 carbene as intermediate. Here, by providing this, which one is reduced? CH2 is the carbon is reduced. Okay, I was originally I1 minus. This was a 0. It forms here. This becomes a plus 2. Metal was oxidized. The carbon was reduced. Okay. So this CH2 formed. Now it can form. It can react with this double bond and very clean tricyclic structures. It has a CH2 here, but if you just roll, it's simply like this. So this reaction is called, is named reaction Simmons-Smith reactions. Maybe two chemists invented this reaction together. So we learned two carbene reactions. One is chloroform with a strong base. Then we can get CCl2 addition. Simmons-Smith condition, CH2I2 and reduction. Then it forms this carbene as an intermediate. And it forms this kind of insertion reactions. Carbene reaction. Today we learn one more. Radical reaction. We have learned the radical reaction before with alkane. So if we have alkane and easy breaking material like a chlorine with energy, then it can form this. Starting step was breaking weakest bond and it generated a radical. The radical attack, radical is very reactive. The radical attack alkane, and it generate catch up this H dot to make HCl, and it generate the alkyl radical. In this step, we said H dot may not be formed because H dot is more unstable. Okay, that's why H dot is captured right away to this, and then alkyl radical was formed. This alkyl radical can react with another Cl2. It forms this product, and then regenerate another radical. So this was propagation reactions following this cycle. So this cycle reaction is the product is alkyl halide was made. With that reaction we have learned as a radical reaction. Now if that kind of condition happens to double bond, what happens? In alkane case, on this bond should be broken, and then one going here and one leave here, but that was consumed by another reagent. But if it is an alkene case, it does not stop. It keeps going and it forms this kind of a long chain, so-called polymer. So the mechanism, the first step is we need to initiate the radical reactions. So previous case, Cl2 has weak bond, it was the break in the middle. It can be used as initiator too. But as we said, Cl2 chlorine gas is toxic gas. We don't want to use it. So instead of that toxic gas, or reagent, peroxide. Okay. Alkyl ROO or carboxyl acid OO, it doesn't matter. Those are the peroxide, easy breaking in the middle, and it can generate radical. And that radical attack first. Any radical attack first of this bond. If there is an alkane, just capture one proton, it generates the radical. But in this case, it has two electrons there, two extra electrons there. One is making this bond, and the other one leaves here. After reaction, still radical is on that molecule. That means that reagent, after first reaction, this is the first reaction, and the still radical is there, and this radical can react with another molecule. And if it forms here, bond forming here, and then this radical is again regenerated here. It doesn't die. The radical is moving to the next and next. So the reaction is, this is also a propagation reaction, but it's in the molecule is propagating. Because it has a double bond character. And it can donate one electron here, one electron here. Okay? So that's the big difference. Alkane case, once this radical is formed, react with another motif, and then the radical disappears. That's why single molecule is formed and clear. Reaction finished. But alkene case, this radical does not die. It's living, continuously reacting with others to make longer and longer product. So this is the so-called polymer formation. So polymer formation, different mechanism there too, but one case is any double bond, and then you provide radical initiator. Then until the radical is died out, it can continue to forming out this polymerization reaction. It can form long polymers. So depending on the starting material, if this is a propylene, recall this is a polypropylene. Polypropylene structure is long chain with alternatively active nucleic. Polyethylene, what can be the structure? It's one of the most common polymer structure, polyethylene. Polyethylene is CH2, CH2. If that forms a polymer, what can be the structure? It's just a simple long alkane. Nothing attached, and it's just a long alkane. Okay? That's a polyethylene structure. Polyethylene usually chemically very stable because it's a simple polyalkane. That's why there's no functional group. That's very stable. Polypropylene is also alternatively methyl, CH2, methyl, CH2 is alternative like that. This is also very stable. Polyethylene, polypropylene, they are quite stable. Now, this is styrene. Styrene case is forming like this, and alternatively there's a family group. Comparing to this is a little bigger group in both sides. Maybe density can be a little lower, a little more flexible, and a little shiny too. So that's why polystyrene, the materials are very commonly used in our life, but that's a little physically a little weaker and chemically a little more reactive than polyethylene and polypropylene. Okay. So this is the one reaction we need to know in alkene. Comparing to electrophilic conditions, we have learned that this basis, protonation and activating to make a carbocation, and then that carbocation react with the nucleophile and reaction is finished. Okay. One is intermediate is formed and then attack finished. Radical reaction, and once it is a react, then that radical does not die out. It's just the position is shifted to the next and next, and it can go for the polymerizations. So this one we can compare that with the alkene case too. Okay, now last topic. Now through these hydration reactions, by adding acid and water. So we started this reaction from last week. Acid addition here, and then it forms carbocation intermediate. And that carbocation has a sp2 structure, planar structure. Then that position can react with the water, and water can come either from the top or from the bottom. depending on those attack side, it can form two different stereoisomers. In this case, this is enantiomer. Ratio, theoretically, it should be 50-50 because it's a fully planar and there is no discrimination coming from the top or from the bottom. In a sense, this is kind of a prochiral position. Now, by adding one hydroxyl groups, it generates stereoisomers for racemate, unless the fully the mixture. If you do hydroboration reaction, what product would you expect? Hydroboration and workup, then what product would you expect? Racemate mixture, similar way? Only one, because that water is added only end position here, and there is no stereo center is formed. Oxymercuration, you will get similar result like this. Okay? That's Markov-Nikodym of the reaction condition will attack these positions. So the explanation is that the intermediate is a carbocation intermediate and fully planar, and the attack side is from top or from bottom. It should be 50-50. Now, if this reaction happens to pre-existing chiral center, reaction position is here, and the hydroxyl attack position is this position. Okay. Now, what can be the product? Previously, it is only one hydroxyl group attack and then generate the enantiomer. In this case, if there is a pre-existing chiral center there, then we have one hydroxyl group here, then this position is fixed. It's the R configuration. But this position will be half and half, R and S. Right? Then those two products, what is the relationships of those two products? They are diastereomers. One is the RR and the other one is the RS. Diastereomer can be formed. In this case, reaction, the amount may not be exactly 50-50. Depending on those bulkiness of these, attacking from top or attacking from bottom can be slightly affected too. Okay? But in principle, you will get mixtures. And those are not enantiomer, those are diastereomers. Okay, I think this is the last, so this is summary page. I showed you this page when we started that this chapter. It looked quite a lot, but now we learn them all in the seminars. So last week or before midterm exam, we learned these conditions. HX addition, then by adding protonation, it forms carbocation intermediate. For the carbocation, we don't assume cyclic intermediate. It's kind of open, only one position is protonated. The other position is carbocation. More substituted position was more preferred. Okay. Then X can be added there. Markov-Nikodym rule. Okay. If you add water here, maybe instead of this X, OH can be inserted. Right? That reaction we have learned before midterm exam. When we started this chapter, we learned X2 addition. If you have X2, X can be dissociated 1X plus 1X minus. X plus added to the double bond, forming cyclic intermediate, like a bromonium. And then the other X minus can attack from behind and ring open. Anti-addition. 1,2 hollow, but that's anti-addition. Okay. And if you have water there, then only first part activation happens. Second attack is done by water. Then hollow hydrogen. Hollow hydroxyl compound. One hollow, two hydroxyl compound. Is it anti or syn? It's an anti because this is also cyclic intermediate and they're attacked from behind. Anti-bond. Okay, that's what we learned here. Up to here. So by adding x2, 1, 2x, and then this one, 1x, and then OH attack here. Even though there is a drone on the same side, the manner of addition is anti. And then Now this is a hydration reaction. Hydration reaction, we learned basic condition is acid and water, but to control it more specifically in the laboratory, two methods was there. Oxymercuration, hydroboration. Oxymercuration and second step is a demercuration. It's a two-step reactions. Hydroboration and deboration. In oxymercuration, water is oxymercury, means oxygen and mercury was added together. Oxygen was introduced in the beginning. And second step was remove the mercury reductively. You can think why should it reductively? Okay? If it's oxidatively, deposition also OH will be introduced. So to remove mercury reductively, borohydride reagent will be used. Hydroboration, H and H2 was added, and this pH position was removed by oxidative cleavage. Then oxygen was added there. Okay. So that was hydration reaction. Oxymercuration was monochlorochemical. Hydroboration was anti-monochlorochemical. And then hydrogenation. Condition was hydrogen gas or metal catalyst, palladium or platinum. Addition manner is a syn addition, same reaction. There was a reduction or hydrogenation. And today we learned a bunch of oxidation. First reaction we learned was reaction with the peroxide, H2O2 or R4OH. Then epoxide is the product. Epoxide actually has another name. Epoxide or oxidane. Time to time we use both of the names. Epoxide and oxidane. So H2O2 condition gives this form. And then to double bond, to break it up by adding ozonolysis. Depending on the finishing up, ozonolysis break up and then each position CO double bond generate for two ways. One is reductively, then aldehyde. Here is the oxidatively, then acid. Okay, that was ozonolysis. 1,2-hydroxyl addition, what is the condition? Syn addition of from alkene to 1,2-hydroxyl, the group generation, what is the condition? OSO4. Okay. Osmium tetroxide. And to recycle OSO4, what would you use? NMO. Okay. And morpholine oxide, NMO reagent you could use to recycle it. Another reagent we learned from here to move to this. From 2-hydroxyl to 1,2-diol, go to breaking up, what reagent could you use? Periodate. Ozone starting from here directly go here. Okay. Here for 1,2-diol to go here, IO4 minus. And reductively it's finished to generate aldehyde. And one more we learned permanganate, MnO4. It break up everything, generate all acid. Break up the double bond and phosphorize the oxygenate, CO double bond, and then everything is oxidized to generate the acid. So that's all we have learned today. One more thing, carbon. So we learned the carbon today. C dot dot reagent, carbon. That can make cyclic propane. So two reagents. One reagent was chloroform with a strong base. Then CCl2 could be added. Sometimes we don't want to have a chloro. Then Simmons-Smith reagent, CH2I2, reduce it by metal, zinc or copper. Then CH2 carbon will be generated. Then you can react with that. And polymers. Okay, this is all we have learned today. It's a little much. This is a critical time. Okay. So you should practice and compare what you have learned so far. 하나씩 따로 공부하면 정리가 잘 안 돼. 문제 풀면서 딱 봤을 때 이거는 이해에 해당하는 거니까. Of course, the real situation is much more complicated than this, but you don't require that much. I will give you only defined conditions. Which one is the intention of professor is something you need to catch. Markov Nikov or anti-Markov Nikov. Breaking up the double bond or oxidize to different reactions. Okay? With this several grammar, you can make many combinations. So that's why it's important to solve the problems and think and make the logic in itself. Okay? 바쁘겠지만 이번 주말 동안은 이 챕터를 꼼꼼하게 문제를 많이 풀어보면서 필요하면 더 풀어봐. 또 같은 거 다 풀어봐도 좋아. 그렇게 해서 다음 시간에 좀 해주면 좋겠어. Okay, we are here now. So we just finished the alkene reaction. Next week, we are going to study alkyne triple bond. Interestingly, double bond is more reactive than triple bond. Triple bond has a one pi electron, the other pi electron like this. That's actually a little more stabilized. So most of those the reactions we learned today will be applied to this with a little harsh conditions. After that, we move to the alkyl halide and the reaction of alkyl halide. We already started a little of alkyl halide. Like this. This is attached here and it is removed to form the epoxide. Okay, this kind of this reaction is an intramolecular reaction, the same molecule, but we are going to learn about intermolecular, molecule to molecule reaction systematically. So there are more mechanism study about this. After that, we are going to study several technique of molecular characterization. Okay, then we can finish. So, not too much. We learned almost half of those reactions today. A little application to alkyne next week. Then maybe the other half of study will come here. Okay. That's the organic reaction that we are going to learn within this semester. 공부 안 하면 정말 따로 배웠다. 지금 공부를 해야 수업 시간이 즐거워집니다. Okay. Okay, let's finish here.